Predictive Smart Maintenance Seminar Series. My name is Madhav Misra and I am hosting this seminar. Today we have a speaker from Singapore, Dr. Nagarajan Raghavan, who is going to share his work on the topic of on-the-fly remaining useful life prediction for electronics devices, combining Bayesian and data-driven approach. Dr. Nagarajan is an assistant professor at the Singapore University of Technology and Design, and he is leading the Nano Micro Reliability Lab. Dr. Nagarajan was a postdoctoral fellow at MIT in Cambridge, USA, and at IMEC in Belgium. He obtained his PhD degree in mechatronics at the Division of Macroelectronics NTU, Singapore. His work focused on prognostics and health management for electromechanical failures, predictive maintenance, design for reliability, life cycle management of microelectronics, device physics of failure, etc. And presentation will take around 40 to 45 minutes, and afterward we will have some time for question and answers. So we are excited to listen from you, Naga. So please, floor is yours and go ahead. Yeah,
Sure, thank you, Madhav. Let me just share my screen.
I will just.
Can you see my screen, Madhav?
Yes, we can see. At least I can see now.
Okay, okay. Okay, good afternoon, everyone. Thanks to Madhav and Rice Institute in Sweden for giving me this opportunity to be part of this AI for PDM series. As Madhav introduced, my name is Nagarajan Raghavan. I'm a faculty at the Singapore University of Technology and Design. We have a department called Engineering Product Development. So I'm part of this department, which is a mix of electrical, mechanical, healthcare design, aeronautical engineering, and material science as well. So it's an interdisciplinary department that we have, and my expertise is basically on statistical modeling, prognostics, and health management. And I basically apply these to reliability study of nano electronic devices and microelectronic devices. So my talk today is also going to be something related to this. So I shall basically introduce my institution to you, and then talk about what we do in our research group, and then I shall go into the topic after that. So the title of my presentation is "On the Fly Remaining Useful Life Prediction for Electronic Devices: Combining Bayesian and Data-Driven Approaches." This is the work that was accomplished by my student Kargoili, who recently graduated from my research group. I will be presenting the work that was done by her. So this group that we have is based at SUTD. So SUTD is a public research university in Singapore. It's the fourth university that was established in Singapore. Singapore is a very small country. We only have 4 to 5 institutions here, and this is the fourth institution set up by the Singapore government. And we kind of different from we are different from the existing institutions in Singapore like NUS and NTU. Our focus is more on design oriented technology development, and we believe in design oriented education. And most of the courses we offer and most of the research we do is highly interdisciplinary in nature. So that's the reason why our departments are also not split into different standard silos of engineering, but we basically have product design, system design, architecture design, and information systems design. These are the 4 different departments in our university. We were jointly set up by MIT and Zhejiang University in China. So MIT has 3 institutions worldwide that they helped set up. One was in Singapore, which is SUTD, and then the other 2 were in Russia and in Abu Dhabi. So this is one of MIT's flagship institutions that was set up in 2009. We have a beautiful campus, and you're more than welcome to visit us if you come to Singapore. We are based very close to the Singapore airport. So we're just a couple of kilometers away from the runway. So it's a beautiful campus, very close to the airport, and we have around 2,000 undergraduate students on campus, and around 1,000 graduate students on campus as well. So that's basically the size of a university, and we have around 125 faculty members in the different schools of engineering and tech and design. So a brief bio of myself. So as Madhav introduced, I was in microelectronics was my basic field of research. I did my PhD in microelectronics in NTU in Singapore, and then I was in Belgium, and I was also in MIT for some time, and then I returned back to Singapore for my faculty job. And I've been a faculty here for the last 6 to 7 years, and my research spans different topics, including reliability modeling of electronic devices and systems, physics of failure, design for additive manufacturing, and material design and reliability as well. So we basically kind of look at how physical models can be built and how these physical models for failure can be combined with statistical approaches to uh, better predict the lifetime of different nano and microelectronic devices, because many of these devices have very complex failure mechanisms which cannot simply be modeled by simple physical models. So we kind of need the help of machine learning techniques as well as physical knowledge to kind of hybridize these two different approaches and see how that can help us more accurately predict the lifetime of different electronic devices. So that's the main focus of our group here. So my lab is basically called Nano Macro Reliability Lab, and as the name goes, we kind of look at systems that are nano in size, be it transistors or data storage devices or microsystems like LEDs, all the way to macro systems, including looking at power grids and transportation systems and additive manufactured devices and so on. So we kind of look at reliability across the whole horizon from nano to macro level. And of course, the tools and techniques we use are pretty much the same, whether it's nano or macro. But of course, they have to be tweaked and modified according to the kind of systems we look at and how complex they are. And our group focuses not just on analyzing and predicting the reliability of these devices, but it also we also trying to look at how we can redesign these devices to improve their lifetime and life cycle by more carefully understanding the fundamental root cause of failure that will help us design better devices for more robust field use applications in the future. And if you want to find out more details, you're always welcome to look up my research website, which is shown here. So this is the outline of my presentation. I shall give a brief background of the field of PHM, which most of you are very familiar with. And we shall look at different schools of how prognosis can be done, different methods of prognosis. And then I shall talk about the motivation and research objectives of this work here. And then the actual execution of the work is split into three different sections. For the first section is where we talk about model-based prognosis using particle filters. And then the second section is where we look at the hybrid prognostic algorithm, where we kind of combine particle filters and neural networks in a certain fashion to achieve certain end results in terms of remaining useful life prediction accuracy. And the last part of my talk will be looking at how physics can be infused into the hybrid prognostic algorithm to get the machine learning models or neural networks to understand the logic behind the dependency of different factors in the failure mechanism and learn in a more smarter way rather than just learning brute force by feeding data into it. So these are the three sections of my presentation, and then I shall end my presentation with the conclusion and touch on what future work we are kind of looking at right now, and also some relevant publications that you can refer to. So moving on to section one on the background, we all kind of know how important maintenance is and how much financial impact it can have, and also what kind of safety impact it can have on the operation of different systems on the field. And these are just a few examples which I don't have to go through in detail, but I think we all obviously know that the financial impacts and the social impacts of any incident, untoward incidents, can be very catastrophic. And in order for these devices or systems to be maintained well enough, and maintained in a robust manner, it is important for us to have techniques and methods and technologies and sensors to be able to estimate the remaining useful life of these devices. Because without the remaining useful life prediction, there is no way we might either be over maintaining the system or under maintaining the system. So it's important for us to have a good gauge of when the likely lifetime of the device is for the next failure. And based on this remaining useful life, we can accordingly schedule the maintenance actions and ensure that the system's availability is kept high and it's chances of unexpected failures are kept as low as possible. So this is a standard chart that we are all quite kind of very familiar with, that touches on the different schools of maintenance, ranging from corrective to preventive to predictive maintenance. And as I just mentioned to you, predictive maintenance has been enabled by multiple different factors, including sensor technologies, Internet of Things, and the Industry 4.0 in general. And one of the key components of predictive maintenance is prognostics. And the key enabler for predictive maintenance is our ability to come up with models. It could be physical models, machine learning models, it could be phenomenological models, it could be Monte Carlo simulations, it could be finite element models. We kind of able to model physics, model failure mechanisms better these days with all the computational technologies that we have, and with all the computational power and the power of computing that we have right now. And that has become a key enabler for us to be able to make on-the-fly prediction of remaining useful life for many critical devices and systems. And that in turn enables us to implement predictive maintenance in a more holistic and robust manner, basically. So, a few key terminologies that I think we should all be quite familiar with. Remaining useful life is one of the key metrics that we always talk about, which is nothing but the remaining time left before a particular system or component's degradation level hits the threshold that is defined by the user. So, this failure threshold is defined by the user, and it is up to the kind of field specific applications that the device is used for. These thresholds can always depend on what kind of field applications they are used for. And based on the current data that we have collected from the sensors that are on the system being used, we kind of use statistical methods or machine learning models or physical models to be able to predict the future trend of degradation until it hits its threshold. And this remaining time until it reaches the threshold is what we call as RUL, or remaining useful life. And as we can imagine, it's not a deterministic metric, but it has its own stochastic nature as well. So we kind of not just looking at the mean value of the remaining useful life, but we're also looking at the distribution of the remaining useful life for any given device or system for a particular application at a particular instant of time. So this is the starting time of prediction. And as you collect more and more sensor data, your remaining useful life estimations will keep changing in a dynamic manner. And the benefits of PHM, as we all know, is to maximize the system availability and reduce the failure rate. And when maintenance and optimize the frequency of maintenance, which in turn also means that we're reducing the maintenance costs and life cycle costs of the system, and to extend its operational life to as long as feasibly possible. And I think this is a very simple illustration of why prognostics is important as compared to a traditional reliability approach. We all know that reliability techniques rely on a large sample of population of devices from which you collect failure data and analyze the statistics of failure. But prognostics talks about the individual customized degradation trend of every single device that's being tested. So you're kind of, assessing each component or system on its own without just relying on inference from a population. So in that way, prognostics gives you more first-hand customized information of every single device that is being used in the system, and it's a much better approach to ensuring that the system is available and functional as compared to a traditional reliability approach, which looks at a population of devices to make inferences most of the time. So in terms of prognosis methods, there are three different schools of RUL prediction. One of them is what we call the model-based approach, in which case you have an analytical model or a physical model or a phenomenological model of the failure that's happening. So it could be based on fundamental physics that's already well known, or it could be based on a hypothesis that we come up with, or it could just be an empirical model as well. So it just depends on our level of know-how of the particular component and its physics of failure. You can always come with a model that describes the physics of failure, and this model can then be embedded in a Kalman filter or a particle filter or any kind of Bayesian filtering technique. And when this is done, you can actually use the model and then leverage on Bayesian methods to predict the remaining useful life. This is what we are going to talk about in the first part of this presentation. The second technique is what we call as data-driven methods, which is nothing but using artificial neural networks or Gaussian process regression or LSTM models or whatever it is that we have to use. And these data-driven techniques pretty much rely on historical failure data or real-time sensor data or both of them to identify the degradation trends, time series trends. And in most cases, we don't have much prior knowledge of the failure mechanisms. And that is why we basically go for data-driven methods. So if you have a lot of data, but you have no or very limited physical or technical know-how of the physics of failure, then data-driven techniques, are the best option to choose. And if you have a little bit of both, for example, you kind of know what the physics is, but you don't have very precise knowledge of what exactly is happening, but at least you kind of know what the root cause of failure is, what's the key driving factor that is causing the failure to happen. Is it temperature? Is it joule heating? Is it current over spikes or whatever it is? If you have some idea of what the likely driving force for failure is, then at least you can come with some kind of a model that describes the failure. And if you still have data coming on board from the sensors installed in the component or system, then it makes sense for us to leverage on both the data and the model. And in such scenarios, we basically call it as a hybrid prognostic approach. So we will kind of deal with model-based approach and hybrid approaches in this presentation, as we will see in the slides that will be shown in the next few slides. So coming to section 2, let's look at the motivation and research objectives. So the reason why we are looking at electronic devices and systems in general is because many electronic devices have a very complex trend of degradation. For example, in this case, I'm showing an example of light emitting diodes. And light emitting diodes are subject to degradation due to multiple different factors. It could be due to moisture ingression into the package encapsulations. It could be due to luminosity degradation due to dust particles. It could be due to other environmental factors as well. It would also be because of internal temperature rise and joule heating effects and so on. So there are multiple different driving factors that cause luminance degradation of LED devices, and that is kind of evident in this trend that you can see that you see a gradual degradation in the light output followed by an abrupt reduction in the light output by around 5 to 10%, followed by subsequent gradual degradation once again. So you can see that such complex degradation trends are repeating themselves for multiple different LEDs tested under controlled conditions. So this is not just a trend you see in one single LED, but this is a trend that is being shown by a population of LEDs belonging to a particular technology that's being tested at a particular set of test conditions, basically. So you can see that this kind of phenomena cannot simply be described by a simple exponential degradation model or a simple power law model, because it does have gradual degradation trends, but it also has some catastrophic jumps at different locations. And these jumps and these complex trend of gradual degradation plus catastrophic jumps cannot simply be modeled by a very standard analytical model. So you kind of have to account for these complexities in the degradation time series data. And in order for these to be modeled, we kind of need better prognostic algorithms for us to do the remaining useful life prediction more accurately. So a single methodology might be inadequate for such scenarios. And the main reason, as I mentioned, is electronic devices are subject to electrical, thermal, and mechanical stresses. And these electrical, thermal, mechanical stresses are coupled with each other, and one aggravates the other, and that causes the whole degradation physics to be quite complicated and intercoupled with each other. So in such cases, it could be difficult to even measure the failure, or the failure could be embedded in the it could be latent. It may not even be apparent to us that the failure is likely to happen in the near future. So it's kind of not that easy to be able to do prognosis in some scenarios for electronic devices. And you could also have scenarios where the data being collected is not obtained at regular frequencies of sampling intervals, or the data might actually make sense only when a certain sufficient amount of data is collected, because devices usually function well during the initial phase of its life, and then subsequently their degradation trends can be quite haphazard. So it's not easy for us to come up with a single model that describes the whole time series degradation pattern that easily. There are also challenges in prognosis. One of them is basically the uncertainty in the degradation model. As we all know, any model that we come up with is based on some fundamental set of assumptions, and these assumptions are questionable. They don't really hold true all the time. So we make some assumptions, we make some hypotheses, and we come up with a model. But we still need to make sure we still need to be aware that these remaining useful life predictions that are based on these models are only true if those assumptions hold true for that particular application and end use case scenario. So these are all things that we should be aware of. And the physics of degradation can also change as the degradation state of degradation changes. So depending on whether the battery has 80% charge or 60% charge or 40% charge, the physics of failure in the battery itself can be very different. That's battery is a good example for this. And even these model parameters in the model that we physics of failure model that we come up with are very much dependent on the material properties that the device is made of. So, all these different factors have to be accounted for, and these uncertainties have to be embedded in the degradation model when remaining useful life predictions are made. And when remaining useful life predictions are made, these stochastic estimations have to be accounted for to ensure that whatever maintenance policies are developed, there is also an accountability that remaining useful predictions are just stochastic estimates and not deterministic estimates. So we have to have a buffer in the maintenance policies depending on what kind of distributions we see in the remaining useful life estimations. The other challenge here is that we always have to make a compromise between accuracy and computational complexity, because model-based methods have might be good in terms of computational complexity because you kind of have the physical knowledge embedded in the model. But if you're using techniques like Bayesian filters, they actually are computationally quite intensive. So there is a compromise you need to make on what kind of complexity you want in terms of computation and what kind of accuracy you want to achieve as well. Same thing goes for data-driven techniques as well. The higher the quantity of data available, the more complex your learning process becomes, and the architecture of the neural network is also very much dependent on all these different factors. So there's always the delicate compromise between accuracy and computational complexity, which is a fundamental challenge in prognosis which we have to live with. So the key research objectives of this presentation is to identify suitable model-based and data-driven prognostic methods which can handle degradation trends in complex systems, which can handle complex degradation trends, and to identify the strengths of data-driven methods and model-based methods and see how we can hybridize these two methods, how we can take advantage of both data-driven and model-based methods to develop hybrid prognostic algorithms that can actually give us better predictions of remaining useful life at a in a preferably less computationally intense manner, basically. And we also want to check the applicability of our proposed hybrid algorithm on multiple different electronic devices and systems to make sure that the algorithm that we propose is not just applicable to one single system, but it's kind of a generic framework that can be used for many complex failure scenarios in different systems and devices in the field. So we don't have a testbed in-house here. So we basically rely on open source data sets to validate most of our prognostics frameworks. And these are the four common data sets that we kind of look into to validate most of our frameworks. We look at battery data sets from NASA and Center for Advanced Life Cycle Engineering in Maryland University. We look at power MOSFETs, light emitting diodes, as well as crack propagation in composite materials as well. So these are four different use case scenarios that we commonly use. And of course, these scenarios are also chosen because these are specific components or devices where the trends of degradation can be quite non-monotonic and quite complex in terms of the trend of degradation. And these, in that way, also end up being good, robust and difficult data sets for us to validate our frameworks with as well. So let's talk about model-based prognosis to begin with, where we're purely looking at a model-based technique where there is no machine learning involved. We're just looking at a physical model that describes the failure of a particular component or system. And we want to see how the particle filter technique can be used for remaining useful life prediction for these kind of scenarios. So this is a flowchart that talks about the different scenarios of prognosis that we might encounter when we use Bayesian inference. So if you have a linear degradation process, then we basically use the Kalman filter, which is the most traditional filtering process that we have all learned in our high school, in our undergraduate school days. And if the process of degradation is non-linear, then we can't use the Kalman filter. And that's where we have to look at whether the system's noise patterns are Gaussian or non-Gaussian. If the system's degradation trends are Gaussian, then we can either go with an extended Kalman filter or unscented Kalman filter, which are nothing but linearizing the non-linear models to kind of still use Kalman filters principles to do the prognosis. So that is possible if you can live with the assumption that Gaussian distributions are what govern the measurement noise and the system noise and so on. But if the system and measurement noise are non-Gaussian in nature, then we basically go with particle filters, which is the most generic approach you can think of. And particle filters have their own advantages because they are suitable for highly nonlinear systems and non-Gaussian noise scenarios. And if you don't have a clear idea of whether a particular new system's degradation patterns are following a Gaussian trend, whether they are, whether the degradation physics can be linearized or not, if you don't have prior knowledge of these facts, then I think it's a safe bet to just go for particle filters because it's the most non-ideal generic framework that can be applied to any kind of failure patterns in general. So in that sense, particle filters is a very generic and good framework that can be leveraged on, and that's the reason why we are focusing on it over here. And it is suitable for scenarios even when the amount of degradation data available is quite minimal. It still works well as long as you have a fundamental model or a simple model that can describe the trend of failure or degradation of the device or system, basically. So this is the particle filter framework that we are focusing on over here. So let me just briefly introduce how the particle filter algorithm works. I'm sure many of you might have seen this in multiple different articles and review papers and so on. But I just want to give you a brief flavor of what happens in the particle filter algorithm. So you have what we call the sequential Monte Carlo technique here, where you have a model for failure or degradation, and this model has parameters in the model, and these parameters have certain values, right? So the values of the parameters in the model can be described by these particles here, and these particles have a distribution as well. So for example, if you're looking at activation energy as a particular parameter in a material degradation model, then you may want to assume that this activation energy has a range of maybe 3 to 5 eV, for example, for a particular failure mechanism. And this range of activation energy is represented by these particles that describe the different values that the parameter in the degradation model can take. And as and when you, and of course, you kind of, take a posterior distribution of the parameter values of the model from the previous cycle of sensor data, and then you get a new prior from it. And then when you get a new measurement data of the system that is being monitored in real time, you basically update your likelihood of this measurement data, belonging to these parameter values. So these blue circles here represent the updated values of the model parameter values, and you're trying to estimate the likelihood that this new measurement data corresponds to these different model parameter values. And obviously the likelihood that this blue circle represents this red data is much higher because they are closer in proximity to each other, and therefore the likelihood values for these data closer to the measurement data would be much higher in value. So therefore you kind of estimate the likelihood for all the different model parameter values. And subsequently, what we do is what we call as resampling, which means that you kind of preferentially take more model parameters values that have higher likelihood and ignore the values of parameters that have a lower likelihood value, which is what we call as resampling. And once this resampling is done, you have a new distribution of the posterior values for the model parameters. And then you successively do this repeatedly for every new cycle of measurement data you get from the sensor. And as you do this for as many cycles as you want, you basically keep updating your posterior distribution of the model parameter values. And with this posterior distribution, you can basically plug it into the degradation model and estimate what the different traces of time series degradation are likely to be for the different values in this posterior distribution. So you can, with this posterior distribution, you can estimate the different traces of degradation that the system is likely to take on in the future of the system's degradation pattern, which will in turn give you the remaining useful life prediction of the particular device or system. So this is the basic fundamental principle behind how particle filters work. And where does the degradation model come in here? So this is the previous posterior distribution represented by the gray dotted lines, and the new posterior is represented by this orange color distribution over here. So we have two different functions in the particle filter algorithm. One is called the state transition function, and this is where the physics comes inside the picture. So the physics of the model, be it the resistance degradation of the battery or the lumen degradation of the LED device, or the crack propagation, the crack length of a composite material. It could be any kind of physical parameter that you're trying to measure. And the fundamental model that governs this physical process is embedded in the state transition function. But we don't embed it as a standard model, a standard physical model, but we actually make it as an incremental model, which means that, let's say, for example, we take batteries as an example. So I need to come with a state transition function that tells me what the resistance in the kth cycle of the battery is as a function of the resistance in the k-1 cycle of the battery. and maybe it's state of charge and state of health or something like that, for example. So this state transition function is an incremental model that relates the degradation at time k as a function of time k minus 1 in a physical manner. That's basically what the state transition function is trying to do. And then you have the measurement noise described by the second equation. And then you have the likelihood function that's given by this standard expression here. So this is where the physics comes into the picture. And then with this resampling process that I showed in the previous slide, you can basically predict the future trend of degradation of the system. And when the trend of degradation hits the threshold, you can basically estimate the remaining useful life. And this particle filter method not just doesn't just give you a single value of remaining useful life, but it gives you the whole distribution of what the different likely RUL values could be for a particular scenario of degradation. So it gives you the stochastic of degradation as compared to a traditional machine learning model like neural network, which may just give you a deterministic value of the RUL. So this is the battery data set that we were analyzing, and this particular data set is from Kelsey here. So we kind of tested our approach, and this is the incremental battery degradation model. And these are the data. This is the data that we've collected so far. So this is the time at which prediction is being made after 100 cycles of stressing. And then when this incremental degradation model is fed into the particle filter and you do the prognosis, you can see the dark red dotted lines represent the mean value of the degradation, and the smaller dotted lines represent the 95th and 95th confidence interval of our predictions of the future degradation trend. And this green line represents the threshold at which we kind of classify the device to have failed. And with this definition for the threshold, you can kind of extract the histogram of REL values that would correspond to these different traces of degradation hitting this green line over here. So this distribution is what we basically care about. And this RUL, as you can see, can range anywhere from maybe 180 cycles to 300 cycles. So this is the range of likely values of RUL, and you can also extract the mean and the variance of the RUL from this distribution over here. So so this is kind of the strength of particle filters. As I mentioned, is a stochastic approach, which gives you not just a deterministic value, but a range of values for the RUL. But there are some downsides of the resampling of the particle filter approach as well. One of the issues with particle filters is that the process of likelihood-based resampling that you see here can sometimes end up in very few particles getting selected and many of the particles getting eliminated from the process, because you might realize that just a couple of particles have a very high likelihood value, but many of the others have a very, very small likelihood value. That results in the distribution getting too confined to a particular value in the design space, basically. So this kind of scenario is what we call as particle degeneracy. And when this happens, you basically sometimes end up in a local optimum scenario where the RUL predictions are either not making sense or they are too determined. It kind of doesn't show you the stochasticity well enough anymore. So you kind of have to uh, choose different resampling strategies to avoid this particle degeneracy from happening. So you can see that this is a range of values of the particular degradation state here. But if particle degeneracy were to happen, you can see that most of these states get eliminated, and you just have a very few discrete states that doesn't really represent the stochastic nature of the system anymore. So we kind of rely on other resampling techniques to eliminate this particle degeneracy. I shall not talk about the details of how these resampling techniques work, but these techniques do help us get better remaining useful life estimations. And it turns out that of these different techniques here, like multinomial resampling, stratified resampling, systematic resampling, residual systematic resampling, and partial resampling, we see that systematic resampling and partial systematic resampling give us very good results, as we can see from predictions made at three different time snapshots of 120, 240, and 360 cycles for the battery degradation data set. You can see that the systematic and the partial systematic resampling techniques give us consistently better results as compared to the other resampling methods. The reason why this is the case has been explained in one of our research studies. If you're more interested to know details, I'm always happy to share the article with you later. The other issue that we also end up with is kind of similar to degeneracy in a way, but the problem here is what happens is all the particles get eliminated sometimes during the resampling process, and this again results in particle impoverishment. And this is again because the likelihood value of some particles could be so high as compared to other particles that all the other particles get eliminated from the resampling process. And this is again an undesirable scenario for us, and therefore What we do here is referred to as particle roughening. So we kind of add a Gaussian noise to the resampled particles at regular intervals of time, or during every cycle of iteration, to ensure that the impoverishment issue is addressed. And this again helps us ensure that we get better accuracy of the RUL predictions. So this histogram here represents the relative accuracy of the battery remaining useful life prediction for several different resampling techniques that we discussed in the previous few slides. And you can see the one circled in red here is what we call as the roughening particle filter, which is the last method I talked about. And it turns out that the roughening particle filter approach gives us one of the best accuracies in remaining useful life prediction. And of course, the downside of it is computational time is much higher than the other techniques. But as long as the frequency of sensor data being the acquisition of sensor data frequency is not too high, if it's in the range of a few seconds to tens of seconds or something like that, or a few minutes to tens of minutes, then this time taken to make the prediction isn't a big constraint. But if the sensor data frequency is much higher than the few seconds that we're looking at here, then maybe you got to filter out the data and try to make better use of try to like filter out the data before you even apply this technique over here. So we have shown that the roughening particle filter does have its advantages over all the other resampling techniques, and this seems to be one of the most robust techniques to address all the drawbacks of traditional particle filters that I talked about earlier. So the other scenario where particle filters is very useful is scenarios where we have very complex bimodal degradation patterns, as you can see here. So you have a linear trend followed by an exponential trend of degradation, which is very common in batteries. This is also another scenario where we're looking at crack propagation in composite materials. And for such scenarios, what we need is kind of a technique to find out the change at the point at which trend of degradation is changing, which is what we call as knee point. And we kind of want to see how we can detect this knee point, and how can we embed a bimodal failure scenario in a particle filter framework. And this is where we kind of looked at a two-phase model for batteries. Batteries are one particular example where the knee point detection is a very critical part of the whole battery lifetime prediction process. And we kind of looked at two different models, the linear model for the first phase of degradation and an exponential model for the second phase. And we kind of built in this two-stage degradation model into our particle filter state transition equation. And we were able to kind of find out the point, or the inflection point or knee point at which the failure mechanism is changing its behavior through this algorithm uh, that was an improvised version of the standard particle filter. And these techniques have yielded us much better results as compared to a standard single phase battery degradation model. So you can embed more complex degradation models into the particle filter as long as you can formulate the state transition function carefully. Particle filters can be used for doing prognosis of very complex failure mechanisms in a very seamless fashion, as long as the analytical formulation is carefully tailored to suit the physics of failure, basically. So that basically addresses the particle filter algorithm, which was purely a model-based technique. But as I mentioned to you, there are some drawbacks of particle filters which we have lived with so far. One of them is that it takes quite a lot of time depending on the number of particles we choose. Sometimes we choose 1,000 particles, sometimes we take 5,000 particles. The number of particles to be chosen is kind of arbitrary at this point. There is no like thumb rule for us to determine how many particles would be ideal for a particular scenario. So there is some ambiguity in how particle filters should exactly be used for a particular scenario. And uh, and and the other downside is sometimes it can be computationally quite complex. So we want to kind of ensure that we have a technique that leverages on particle filters, but not just particle filters, but also on the robustness of some machine learning techniques as well. Because one problem with particle filters is, if you don't know the physics of degradation, then you cannot even come up with the state transition equation. So if the physics is not known here, then there's no way you can use a particle filter. So what we are trying to do now is, if you have a new system or a device for which you don't understand the physics well enough, can we still come up with a degradation model that represents the system, although the physics is not known? So how can we do that? This is where neural networks come into the picture. So if you can use neural networks to model the trend of time series degradation of a particular component or system, then the neural network's mathematical model can be used here to replace a physical model, and that can in turn be embedded into the particle filter to subsequently do the Bayesian remaining useful life prediction as we have been doing in the past. So that's the idea behind our next section of the presentation, where we're talking about hybrid prognostic algorithms, where we want to combine particle filters and neural networks in a seamless fashion that leverages on the advantages of both these techniques for better remaining useful life prediction. So this is what we are trying to do here. So first we take a training data set. Let's say you're looking at a LED or a battery, for example, and let's say you have one or two devices of the batteries or LEDs that has completely failed from time zero all the way to time to failure. So you have the failure data set available for one or two devices in the population. So what you can do is, even if you don't know the physics of failure, you can at least feed this training data set to a neural network. And as we know, neural networks are can easily get overfit or underfitted depending on the architecture of the neural network. So we want to be careful in not choosing a neural network that is highly complicated for a simple scenario, and or not do we want to have a scenario where the neural network is too simple for a very complex data set. So we want to optimize the architecture of the neural network before it is even used for training on the data set that we have. And for doing this, we kind of leverage on this technique called the Bayesian information criterion, also called as BIC. So BIC is a very useful technique for us to optimize the architecture of the neural network that is necessary for a particular data set. So you can arbitrarily choose different number of hidden neurons and hidden layers in the neural network and rerun the neural network training process. And for each scenario, you find out what the BIC value is, and the BIC value that gives the lowest value of BIC corresponds to the best architecture of the neural network. So the strength of this BIC technique is it penalizes you if you use an architecture that is very complicated. So if you have too many weights and biases in the neural network, this BIC will artificially penalize the choice of that network, and that is how BIC enables us to choose an optimal architecture for a particular neural network for a particular data set. So that's how we kind of do this process here. So you take the neural network architecture that is recommended by the BIC process, and then you feed it with a training data set of time to failure for one or two devices that you have, and subsequently your neural network gets trained through this process, and then you extract the mathematical model of the neural network and feed it into the particle filter algorithm as a state transition equation. So this is where the neural network's outputs, or the neural network's trained weights and biases, are mathematically incorporated into the particle filter to replace a physical model which we do not have in this particular case. So the physical model in the particle filter is being replaced by the mathematical framework of the neural network. And subsequently, all that we do is just, using particle filters, you can estimate the, remaining useful life. You can find out the distributions of weights and biases of the neural network. So in a way, what we're doing is we are actually training the neural network once again here, is using a Bayesian approach. The Bayesian approach is helping us find out not just the values of weights and biases as deterministic values, but it also gives us the stochastic values of weights and biases of the neural network. So in a way, you're training the neural network in a better way by leveraging on particle filters over here. So once neural network is trained with the particle filter, the weights and biases are trained with the particle filter. You can then use the trained neural network. It's a so-called, I call it the Bayesian neural network, because the weights and biases of the trained neural network are not deterministic, but they are stochastic with its own distributions. So with the Bayesian neural network, or the neural network with stochastic values of weights and biases, you can then uh, use the trained neural network on real-time data for new devices and systems to make the remaining useful life prediction for new devices that you are interested in. So this is how we kind of leverage on a machine learning technique of neural network and the particle filter, which is the Bayesian method. We kind of hybridize these two techniques to make good use of both these methods, and be able to do a stochastic RUL prediction of different devices and systems. And this is exactly what I mentioned to you just now. That this is the mathematical framework of the neural network that goes into the particle filter algorithm. And you can clearly see that this method actually helps us model non-monotonic traces of degradation very well. So this is an example of NASA battery data set. You can see that the pattern of degradation is quite non-monotonic, with a lot of kinks here and there. There are some kinks, there are some gradual degradation, abrupt degradation, and so on. So it's a very complicated time series data set. And with our hybrid, neural network particle filter hybrid method, we are able to achieve very good remaining useful life prediction very early in its phase. You can see that the data here was only collected for the first 40 cycles, and we're able to predict the future trend of the battery degradation all the way till it reaches its threshold of 1 ampere hour, which is far down the road. And you can see that these gray traces, which are our predictions from our algorithm, are very well matched with the black trace, which represents the true degradation pattern of the battery over here. So this is a clear evidence of how this technique makes good use of neural network and particle filters to be able to prognose the failure of very, very complex time series degradation data trends. And we do the same for other data sets here as well. And you can see the comparison of different batteries here. For this is for the University of Maryland data set, this is for the NASA data set. We're basically looking at the root mean squared error value. And you can see consistently that our hybrid method, which we represent as HYA here, far outperforms the particle filter method and the standard neural network method for all the different scenarios of different data sets that we're looking at here. You can see that the RMSE values are much lower when we use a hybrid method of prognosis. So this is a clear evidence that leveraging on particle filters and neural networks in a nice in an interesting fashion, like mixing their uh, uh, advantages in a nice way, helps us gain a lot more prediction accuracy as compared to using just one of them alone. So there is still one issue that we encountered, which was basically the issue of outliers. So as you know, this training process is a very stochastic process, and sometimes you end up with degradation traces that are far away from the true degradation trend. And this is because there is absolutely no physics embedded in the framework to begin with in this process here, right? So what we want to do is to see whether we can kind of infuse some physical knowledge or some logical training into the neural network so that it doesn't do a brute force learning, in a blindfolded manner, but rather it learns with some physical knowledge or some with some smartness embedded into the neural network. And this is where we kind of looked at how physics-informed loss functions can actually be inbuilt into the hybrid prognostic algorithm, so that the neural network doesn't just learn from data in a blindfolded manner, but there is some kind of physics embedded in the training process of the neural network, which is what people call as physics-informed neural networks in many literatures, basically. So in this case, since we are focusing on the battery data set, we kind of looked at one of the common failure mechanisms in batteries, which is called the SCI film formation, which is one of the most prominent failure mechanisms for batteries. And this particular phenomenological model is a very good descriptor for the SCI film formation in batteries. So this is a physical model or a phenomenological model, which we actually incorporated as a loss function into the neural network. And this helps us train the neural network with more smartness, because it understands that if there is a deviation of this trend, if the predicted output of the neural network is too far away from its true value, then the loss function would obviously have a very high value. So this loss function, that is as an additional loss function in addition to the data-driven loss function, forces the neural network to learn more logically. So that's basically what we're trying to do here. So it's the same framework as as what I showed earlier. The only difference here is we are introducing a physics-based loss function into the training process that forces a neural network to follow a logical rule when it makes its predictions for a new device or new system. And this is the loss function here. This is a standard neural network's MSE loss function, mean square error loss function. And we incorporate an extra term into the loss function that represents the physical model. And with this combined loss function, we are basically able to eliminate the outliers that you previously saw. So this is exactly the same data set I showed you earlier, but you can see that the outliers have been eliminated from the data set. And this outlier elimination is purely because the physical knowledge has been embedded into the loss function, which makes the neural network much smarter in the way it trains and learns from the data that it receives. So this is clear evidence from both CalC and NASA battery datasets. Once again, when the hybrid algorithm is fused with the physical knowledge, you can see that the RMSE values that are shown in this column are much lower in value compared to the RMSE values that you would get with the purely hybrid method where no physics was embedded into the model. So incorporation of physics does make a big difference in the RMSE estimations. Of course, we have to compromise in terms of the time taken for the algorithm to run, but still, I think the gain in RMSE is much more significant over here that we can take advantage of. So to come to the end of my presentation, I just want to give you some a scope of future work that we're looking at. So as I mentioned to you, particle filters is a model-based technique which has its own advantages, but artificial neural network, which is a data-driven technique, is very good for learning complex degradation time series data patterns. And we are trying to hybridize both these techniques in our method over here to kind of leverage on particle filters and neural networks for and for different tasks. And this hybrid prognostic algorithm has enabled us to more accurately model very complex failures in electronic devices. And to further eliminate the presence of outliers in our degradation traces, we basically have used the physics-based loss functions that further enable us to completely get rid of outliers in our prediction process. And this method, as you can see, there's a lot of evolution that has happened in this method, right from particle filters to different resampling techniques to hybridizing it with neural networks, and then bringing in the physics-informed loss function. So we have evolved our framework over the last few years until it has reached a stage where it it is giving us very good estimations of root mean squared for square error for LEDs, for batteries, for power diodes, and a lot of other devices that we are working with right now. So for future scope of work, we are also looking at how physics constraints can be embedded in a more holistic fashion, because as you know, failure mechanisms are governed by multiple boundary conditions and initial conditions, and a lot more different models for different failure mechanisms. So we want to make sure we have a better physical way of imposing loss functions to the neural network that helps it train in even more smarter manner. So that's something we are looking at to see how other loss functions can be embedded that still describe physics in a better way for the neural network to learn from. And we're also looking at prognostics as a system level now, because all that we talked about so far is component level prognosis. But if you're looking at managing a fleet of systems, maintaining a fleet of systems, you need to be able to make prognostic decisions and predictive maintenance decisions at the system level. That requires us to look at the RULs of multiple different components that are simultaneously degrading. And you will have to use like heuristic techniques and other methods to address the system level challenges of maintenance and prognostics. So that's something we are focusing on in the near future. We're also looking at not just predictive maintenance, but also prescriptive maintenance. So, as you know, predictive maintenance has its own limitations. It can tell you when a particular system needs to be maintained or attended to, but it cannot ascertain the root cause of failure for you. So, what we are trying to see is we're trying to come up with with better frameworks that not just give us an estimate of remaining useful life, but also enable us to more accurately determine the root cause of failure. And to do this, we are basically leveraging on a technique called Bayesian networks. So Bayesian networks is not like neural networks where the nodes of the network have no physical meaning. Bayesian networks are based on the fundamental physical operation of the system. So the nodes in the Bayesian network represent physical parameters. And when the Bayesian network is trained with the data, you can actually use the trained Bayesian network to do a sensitivity analysis and find out what is the most likely root cause for a particular anomaly to be observed. So we are looking at this Bayesian network as a tool for prescriptive maintenance in the near future, and work is still ongoing on these things. So with that, I would like to come to the end of my presentation. And if you're interested in finding out more about our work, I'll be happy to share some of these articles with you. These are all the work done by Kargoili Pugalindi, who is my student who just graduated a couple of months back. So all these results that I've shown in the slides are the work of her PhD work. And with that, I would like to acknowledge my students, Kargoli in particular, who did most of this work, and also Duong and Harry, who have also been very instrumental in getting these works done. And I would also like to thank Madhav for inviting me to this seminar today. And I would also like to thank my funding agencies for supporting our research over the last 6 to 7 years. And with that, I would like to come to the end of the presentation, and I'll be happy to take any questions from the floor. Thank you.